Hi guys, this is Josh, and this is an explanation of note card number 11, the instantaneous rate of change. So first thing that you want to look at in number 1 is it's giving us two definitions for f prime of a, okay? And what f prime of a is the instantaneous rate of change at a point. So we're probably going to be given a function f of x, and we're trying to find the instantaneous rate of change not of the whole function, like in note card 10, but just at a point, and that point is going to be at a. So if we look at the first definition, it says the limit as x approaches a of f of x minus f of a all over x minus a. So if you want a physical picture or a graphical representation of that, what's happening is we're plugging in different values for x. So let's say x could be 1, and then x is going to be 2, and then x is going to be 3. And essentially we're approaching the value a. And we're using a because that could be any number. So if a is 4 in this case, we have been approaching 4. We've put 1 in for x, 2 in for x, 3 in for x, then we might put 3.5 in for x, 3.9 in for x. And essentially what that's doing is moving the point closer and closer and closer to that point A. It's tightening the gap. It's making the change in y over the change in x closer and closer to dy dx, which just means a really small change in y over a really small change in x. So that limit is there because we're going to try to make a really small gap between the yellow point and the red point. We're basically bringing those points so close together and looking at the limit. And again, we have y values on the top. That's important to notice. And we have x values on the bottom. So this is rise over run. So we're getting a slope out of this. And that's going to be the slope of the tangent line at a. That's what this first equation says. The second equation, really similar. It's just a different way of saying the same thing. F of a plus h minus f of a all over h. And that was the original definition of a derivative that we looked at in note card 9, and then we used the power rule in note card 10, which is what came out of that. But now instead of, if you remember, it was x plus h minus f of x, now a is in instead of x. And that is going to give us, instead of the derivative of a function, it's going to give us the derivative of a point, which is what we're looking for in this note card. So that's why it's f of a plus h minus f of a all over h. And that is the instantaneous rate of change, IROC, of a function f at x equals a. The note card goes on to say in part 2, f prime of a is the slope of the tangent line to f at x equals a. So the slope, in other words, of this tangent line, let's see if I can get it close there. The slope of that tangent line is going to be the result of these two equations up here. Okay? So the slope of that tangent line is really what we're finding with these two equations. And then in part 3 it says one physical example of IROC is the rate of change in position with respect to time. And that's the instantaneous velocity, or the average velocities approach a limit as the time intervals shrink in size. So if we have a function that is measuring the position of the roller coaster, and we want to look at that time interval, and then we want to get that to be a closer time interval, and then an even closer time interval, and then a closer time interval. Eventually, that limit process is going to give us the average velocity of smaller and smaller time intervals. And as we bring that average velocity closer and closer together, we're going to get an instantaneous velocity, which is what it's saying there. And in the example we used at the beginning of the year, we were trying to find the speed of the roller coaster after 3 seconds, or wherever the camera was. That's all that we're doing in step 3. That's the reason we take a derivative at a point, is to find, for instance, the instantaneous velocity of the roller coaster when it passed the camera, so we can get a clear picture. All right, so let's actually try to apply this to some problems now. In part 1, it says, what is the instantaneous rate of change at x equals 2 of the function f given by f of x equals negative x cubed plus 3 over 5x squared minus 4x. Now we could use one of these limit definitions, and if we did, we would find the instantaneous rate of change, but we would get into some really messy algebra. So it's going to be a lot easier to instead find f prime of x and then put the value 2 in for x. So we're going to apply the power rule. The only term that I'm a little bit worried about is 3 over 5x squared, because the x squared is on the bottom. So I'm going to go over here and rewrite this term as 3/5 x to the negative 2. And that's going to make my life easier, because now I've got the coefficient, the base, and the exponent all separate, and it's really easy to see what they all are. So now let's go ahead and write this derivative. If I apply the power rule to the first term, we get negative 3x squared. And then I'm going to apply the power rule to this term, which is the second term, and we get minus 6/5 x to the negative 3 and then last, that minus 4x just becomes minus 4. Now when we evaluate that at 2, the first term becomes negative 12, because we're putting 2 in for x. This becomes minus 6/5 times 1/8, because 2 to the negative 3 is 1/8, and then minus 4. And all of that equals negative 16.15. And you can do that on your calculator if you want to check, but it's negative 16.15. So did we answer the question? What is the instantaneous rate of change at x equals 2 of the function f given by f of x equals that equation? Yeah, we took the derivative, that was this step, and then we evaluated that derivative at 2. So that's going to be your easiest way to find the instantaneous rate of change at a point, instead of using these equations. Okay. Number 2. At a time t seconds after it is thrown up in the air, the position of an orange is given by s of t equals negative 4.9 t squared plus 25t plus 3. Find s prime of 4 and interpret the meaning of the value you found. So again, we want to find s prime of x first, or s prime of t. So s prime of t, and then we're going to just plug 4 in to that equation. So s prime of t is going to be negative 9.8 t to the first power plus 25. And that 3 goes away. because that's really 3t to the 0th, and when we use the power rule, it just disappears. So now we're going to plug 4 in to t, and we get negative 39.2, I believe, plus 25, which is going to be negative 14.2. And I'm going to be careful to put units on this. I know that this is measured in seconds, and we're talking about meters. And that's always going to be the case for these position, velocity, acceleration questions, and we'll talk more about that. But I'm going to say that that's seconds, meters per second. Those are the units. So the velocity of the orange after 4 seconds is going to be negative 14.2 meters per second. So it's going to be traveling down at a speed of 14.2 meters per second. All right, and then last, number 3, and again, this is an AP question because there's some stars, says if f is a differentiable function, then f prime of a is given by which of the following? So we know that this means the derivative at a point. And hopefully we've worked enough with these equations now that you're going to be able to look at these equations and be like, oh, well, I know exactly which ones are derivative at a point. And so let's scan through these equations now. The first one is the limit as h goes to 0 of f of a plus h minus f of a over h. Yeah, this is the derivative of a point. We've worked with that a lot, and hopefully you recognize that equation. That's the derivative of a point. This, number 2, f of the limit as x approaches a of f of x minus f of a over x minus a. That is the derivative at a point as well. Okay, we worked with those on the note card 7 through 10 quiz. So hopefully all of that work has paid off, and now you're like, oh yeah, that's obviously the derivative at a point. The last one, the limit as x approaches a of f of x plus h minus f of x over h. Now this looks like the derivative at every point except for what the limit is approaching. It's the limit as x approaches a, which comes from this equation. And so it's sort of blending a couple of the different limit equations. And by itself, this would be the limit at every point, not just at one point. So this would be kind of looking at f prime of x, except that our limit is as x approaches a instead of as h approaches 0. So this one's kind of a mess. This equation is kind of a mess. It does not represent f prime of a. And so the answer that you should give here is 1 and 2 only, and that's C.